Then let's start. So this is just some updates of our lab sessions. So the first 2 points are some common questions from students. The first one is why we use virtual machine. We have to use virtual machine. The reason is that we have to use the Linux system to support the pipeline. The pipeline is the software platform of our class chip. So this is the answer of the first question. Then the second question is that what is AER? So basically it's a communication protocol for the neuromorphic chips. Then we use the AER command to configure the chip. So firstly, when you want to set some voltages of some circuits or read out the current, you have to send the AER events to configure the circuit. Then you can set the voltages. So do you remember in the first lab, firstly, you set some voltages of the NMOS transistor. Then you get the current. Then there is a question, does this current reasonable or not, right? So at that time, actually, you didn't send the AER event. So you didn't actually configure the NMOS circuit. So what you get is not a correct number. But after you send the AER event to configure the NMOS, then you set the voltages, the circuit is configured. Then what you get is the correct number. So about the AER part, there are 2 documents. If you want to know some details, so let's just show a simple example. For example, there is a document called test circuit. So this is the NMOS of the circuit on chip. So why we select some lines, like select line 5, select line 2. For example, here the gate terminal, the name is like NFT some blah blah. Then you search the name in the chip architecture document. Then you can find here, for example, if you want to configure the input voltage, here you find the terminal. It's select line 2. This is why in the AER command you have a parameter that is select line 2. Okay, so this is the question. Then to update, the first one is that you should finish the pre-lab part before your lab session from lab 2. Then if it's necessary, you can insert some hand-drawn figures to explain the questions. Then the last point is that our lab 2 would be difficult, but it's one of the most important labs. So please come half an hour earlier for lab 2. Otherwise, we're afraid that you cannot finish in 3 hours. It's also difficult for me. Yeah. Okay, so this is all from my part. And also some common questions like what is PN junction and what is the bulk of the transistor? I think the professor can explain much more clear than me. So if you still have some questions after this lecture, so professor is here.
Okay, so let's just draw the cross section of the transistor here. There's a source at one end, a drain at the other end. Above it is a gate. And just the source is where the carriers come from, either electrons or holes, depending on the type of transistor. And the drain is where they fall out. So let's take the concrete case that is an N-type transistor. So it's doped with electron-rich stuff here, and then the substrate or the bulk of the transistor is p-doped. So it's rich with holes. So lots of electrons whizzing around here, lots of holes whizzing around here. That's because you take the silicon atom, and it's joined mostly to other silicon atoms in this crystal lattice through the 4 outermost electrons. And the silicon atom will give up its outermost electrons here with about 1 electron volt worth of energy. It takes about 1 electron volt worth of energy to break one of these electrons free, normally. And since the thermal energy is only about 1/40th of an electron volt, the average energy of vibration is about 1/40th of 1 electron volt. It's a tiny fraction of this band gap energy of 1 eV to get it loose. So that means if you just take pure silicon, then only there's a very few free electrons. And every time you get an electron off, you leave a hole behind. And both the hole and electron can move around like free particles, quantum mechanically. But if you just take pure silicon, there's very few carriers, okay? So what people do is they dope it. They replace the silicon atom. I never remember which is which, but they might replace it with boron. That contributes 1 extra electron in the outermost shell. And now you just have this free electron that can whiz around. It's easily broken loose. I think it's actually arsenic. Phosphorus or arsenic contributes an electron.
I think it's phosphorus.
Yeah, phosphorus, it has 1 extra electron in the outermost shell. The binding energy of that extra electron is very small. It's only about two thermal voltages. Okay, instead of the binding energy being 40 times bigger than the thermal energy, it's only like roughly equal to the thermal energy. And because there's many ways for this electron to be free compared to being bound, there's like a huge number of ways that it can be free rather than bound. It means that almost all the outermost electrons are just free and they're whizzing around. So now it's only about 1 out of 1,000 up to maybe 1 out of 1,000,000 silicon atoms that you replace with this donor atom. And when you do that, you activate it by jiggling the silicon around, heating it up and then cooling it down. You can activate this arsenic or phosphorus or boron. And now you get it either becomes N-doped or P-doped. Okay, so what's happening in this N region here? There's lots of free electrons in here, right? And I'll draw those red for negative. Those will be plus. That means the circle means it's mobile. It's a mobile electron. But every time you get a mobile electron like that, you also get a fixed negative ion. That's the original boron ion. You're missing 1 electron, but you still have the opposite charge in the nucleus, and it's stuck in the lattice. Okay, so there's lots and lots of free electrons here, and here, and down here you dope it opposite. So there's lots of free holes. Sorry, it should be a minus. That's a negative electron, okay? By the way, if I make a mistake like that, correct me. Okay. Here, there's lots of free holes and bound electrons, bound ions, all right? Just atoms that are negative charge. So is there any net charge here? I mean, there's lots of free electrons, but there's just as many fixed ions. So it's N-type, but that doesn't mean it's negative charged. It's just lots of free electrons. Is it clear? They're whizzing around at high speed. Let's calculate how fast they're whizzing around. It's easy calculation. Okay, so I'll just write the thermal voltage. Anybody know that number?
26 millivolts.
Yeah. Not 25 millivolts. We'll just call it 25 millivolts. That's a voltage, but it actually corresponds. Sorry, just a moment. This voltage corresponds to the voltage that an electron falls down to pick up 1 thermal energy. So it has the average energy of every degree of freedom. Okay, so it's actually an energy. It's, even though it's written as a voltage, it's actually kind of you can think of it like an energy level. Yeah.
I just have a question about so the source of the drain. So it says it's neutral charge, so it's neutral. So you have 3 electrons, but the equivalent amount in ions as well.
Yeah.
So the same in the drain as well.
Yeah.
Okay.
You're not applying any voltage yet, right? You're not sticking a voltage on this gate of this source of this drain. Yeah, the source. You have a source and a gate voltage, but you're not applying anything. Everything can
What's
be,
the difference in, like, in composition between the source and the drain? The difference between the source and the drain?
nothing. I mean, except the voltage between them.
But doping,
The source is just, you're going to apply a voltage and that'll determine which is the source of the drain. If the electrons are coming from this end and going into here and falling out the drain, this becomes the source. If the drain's at a higher voltage, which direction will the electrons flow? If this is at a higher voltage, the electrons are negative, remember?
Yeah.
So they actually fall upwards towards higher voltage.
Okay.
Okay, so that means the source of the electrons will be at the lower voltage.
Okay.
Right? Because if this is a higher voltage, which direction does the electric field point? This way, right?
Yeah.
And if the electric field points this way, which direction does it pull the electrons? This way, right? Because they're negative. Okay, so they fall out here. They get pulled in from the source for this end FET. Why is it called an end FET? Because the source and drain are N type. And that's what flows through the transistor. The bulk is opposite, it's P. It has a lot of holes, but what flows through this N type transistor are electrons, not holes. Right? You have the opposite type, right? Which is hole type transistor.
I have a question. You're talking a lot about holes. Does this just mean
The vacancy, just think of it like a bubble in water. In this case, it's a bubble it's a positively charged bubble in this cloud of particles that are free to move. And if you quantum mechanically, it acts just like an electron, although it has a higher effective mass, gets accelerated more slowly by an electric field, like 2 times slower than an electron. But it's just a bubble. It's not a physical particle, but it acts like it in terms of the semiconductor.
okay? And the p-doped one, then there you have fixed negative charges and free positive charges.
Yeah, free holes. There are holes whizzing around here.
A hole's a positive charge.
Yeah, the holes are positive charge. Yeah, because to get a hole, you have to actually take an electron and stick an extra electron onto the atom. Right? So it actually leaves a hole in this cloud of particles.
Okay.
But just think of it like positive and negative charge, it'll be fine. It's just that you can't actually physically get a hole out of the silicon into vacuum.
Yeah.
You know, normally.
those 25 millivolts are the voltage between what and what?
It's a voltage that corresponds to how much voltage the electron would have to fall through to pick up one thermal energy. KT, every degree of freedom of some system at thermal equilibrium has KT of energy. Okay, so actually the electron has like 3 degrees of freedom because it can move in 3 dimensions. Maybe it has some spin or something too. Don't worry about that. The scale of energy is KT, but the voltage that corresponds to is KT over Q. And that's 25 millivolts. That's the voltage that you're going to apply to terminals. And when you apply 25 millivolt change, you're basically changing the potential by 1 thermal energy.
This is assuming we're working at 300 Kelvin.
Yeah, room temperature, roughly. It doesn't vary that much in normal transistor operation. You go from minus 40 degrees up to like 100 degrees. Compared to 300 degrees, that's not a big change. You know, it varies maybe a factor of 2 at most over all range that people use normal transistors. At most a factor of 2. Yeah, so it's always a small fraction of a volt, tiny fraction of a volt. And the binding energy of the electrons, the band gap, is still a volt. It's huge compared to this energy. That's why it's a semiconductor. You have very few, in pure silicon, you have very few particles. It's only when you dope it, you know, with arsenic or phosphorus or boron, that you get this, P or N type material. Okay, so why am I telling you all this? So let's compute how fast, this is actually a cool calculation. Let's compute how fast these electrons and holes are whizzing around at room temperature. How can we calculate that? Because that'll be interesting, right? You think they're just kind of slowly moving around? They're actually very fast. How do we calculate it? It's very simple, right? Yeah.
The kinetic energy.
Yeah, kinetic energy, right? So mv squared, forget the 2, equals kT, roughly. So this is the thermal, this is the kinetic energy, the mv squared over 2, but forget the 2. It's equal to kT, right, on the average. Forget the factors of 3/2 and all, it doesn't matter. We just want to calculate the rough magnitude of the speed. So now we have to just put in the numbers here. Okay. Let's make it simple. We'll put Q here. Multiply by Q. And then we'll stick the M over here. Okay, so let's calculate that. That I know how to calculate, right? That's E minus 2 volts. 10 millivolts roughly, close enough. That's the thermal energy. That's the thermal voltage, right? And what's the unit of charge? How big is a charge in MKS units? This you better know for the exam, right? What's the value of elementary charge?
1.6 times 10 to the minus 19.
1.6 times 10 to the minus 19. Okay, so we'll just say E minus 19. What is it? Coulombs, right? And what's the mass of an electron?
9.11 times 10 to the minus 31.
Now we have to divide by E minus 30. E minus 30 kilograms. Roughly. I know that because I'm a physicist before. Okay, so what does that come out to be? Minus 21 plus 30. So about E9, right? E9 meters squared per second squared. Okay, so V squared, so V is approximately, let's say it's 10 to the 9 if you get it right, 10 to the 10 here. So V is V5 meters per second. I know that's about right. 100,000 meters a second, 100 kilometers per second. That's how fast the particles are moving around. And let's calculate if we have a transistor here. Let's just do it in round numbers again. It's 1 micron long. That's actually a really long transistor nowadays, right? With you know, the latest logic families having channel lengths of 10 nanometers or something, 100 times smaller than this. This is like the kind of transistor you build for analog, like a micron long. So how long would it take a freely moving electron to cross this if it's moving at 10 to the 5 meters per second? So the time, of course, it doesn't do that. It collides and stuff. Well, let's just calculate the time scale. The time of transit, I'll just say T, is, so we have to get the time, right? So it's E minus 6 meters divided by E5 meters per second. Minus 11 seconds. So 10 picoseconds. It's a very short time. Okay, I'm doing that because I want you to just understand what the scale of these things is, how fast things are moving around and what time scale you're talking about. That's 10 picoseconds if it was moving in vacuum, like freely moving and not colliding with stuff. So it's a very short time, 10 picoseconds. Yeah, that corresponds to a frequency of 10 to the 11 hertz, switching frequency. That's why silicon logic can work so fast, right? Because it's a short time it takes the carriers to cross the channels. I don't know if that's helpful. Hope it's useful. Yeah.
Excuse me, where did the E minus 6 come from?
1 micron. By the way, can you guys at the other side see this board at all? Hello? Click the yes on your thing if you can see the blackboard. If you need me to move the camera, write on the chat and then Jinwen will inform me, I hope, if he's still here. Okay. Anyway, this is all going. Now I need to talk about energy barriers a little bit. Now, here you have lots of electrons whizzing around, here lots of holes whizzing around. But here, there's very few holes here and very few electrons here, right? It's only holes, very few mobile electrons. So it's a huge concentration gradient of electrons and holes, huge. Like here, the concentration of holes is millions of times higher than it is over here. Electrons, I mean, okay? So what happens if I take a bottle and I put all the air at one end, you know, so one side's in vacuum and I suddenly release the barrier, the air rushes over, right? Because the air particles are all whizzing around and suddenly the air will rush across to the other side to make it equal. In other words, there's a huge flow of this air from one side of the bottle to the other until it comes to equilibrium again. You know, when there's no concentration gradient. Okay, it's not quite the same here because these are charged particles. So that's why you have to now draw the basic p-n junction to explain this. And you'll see it's really simple in the end. Let's say this is n duct here, and p duct here. And that means, I'll just summarize it here. In the end, you're going to have a depletion region build up. I think positive here and negative here. These are fixed ions that are exposed. And over here, you're going to have lots and lots of free electrons still. Over here, lots of free holes. It may be a different, doping on each side. Here it'll have some fixed ions so that it's equal. It has to be neutral. And here's some fixed positive. Okay. So now because of this concentration gradient of electrons, lots of electrons here and very few here, the electrons are going to rush across to this side. That can't go on. As soon as an electron rushes from here to there, it leaves behind the positive charge. And there's an attractive force between this negative electron and this fixed positive charge. So that builds up an electric field pointing back. It'll pull the electrons back. Same here. Let's start with the holes, right? So the holes will rush across this way because there's a huge concentration gradient of holes. But in the end, what will build up is an electric field pointing back this way that equalizes that flow. Right, until the electric field acting on the holes that there are equals the flux of holes because of the concentration gradient. And so I forgot to tell you one important thing. How can charge move around in the semiconductor? There's two mechanisms: drift, diffusion. I just told you about the diffusion mechanism. If there's a concentration gradient, that causes a net flow of the carrier, right? Just because they're whizzing around at high speed. If there's lots somewhere, then they'll whiz to where there's less, just to equalize it. Just because there's more on one side, right? The other way the charge can move because it's charged is because an electric field acts on it. That's drift current. Is it clear what the difference is? Okay.
Can you repeat what's the diffusion working when there's a
There's a diffusion current anytime there's a gradient of concentration.
so if there's a gradient of concentration,
Anytime there's a gradient of concentration, there'll be a current proportional to that gradient. And it'll be proportional to Q, the electric charge, because you have to get units of charge out of it, times some diffusion constant. That's the flux. Or the current, I guess the current density. Due to drift and diffusion. Due to drift, there'll also be a current, but that current is proportional to the charge density times the electric field times something called mobility. It's just another constant. It's proportional to the amount of charge density times the electric field for small electric field. These are the two mechanisms of current flow. Normally, you don't have to know about these to calculate what the transistor does, but you need to be aware that when you have a p-n junction like this, these two currents are in opposite directions and they balance everywhere exactly, so there's no net current. Okay. So what happens is there's a big diffusion current for both electrons and for holes. But that's put in balance by the electric field acting on the concentration gradient everywhere. Okay, out here, there's no concentration gradient, right? It's all neutrally charged. There's no net current everywhere, but there's no drift current, there's no diffusion current, right? Everything's just uniform. Right in this depletion region here, this so-called space charge region, you have just the bare carrier is exposed. And let's see how this works out. We want an electric field pointing from there to there. So we're going to have pluses here, fixed ions. I'll make the right electric field, right? Pointing to the right. Every time you have a pair of such fixed ions, you get a little field line connecting them. Right? It points from the plus to the minus. Okay, so anyway, inside that space charge region, there's this huge electric field. I mean, millions of volts per centimeter. or at least hundreds of thousands of volts per centimeter.
And you just said that these are the fixed particles. Aren't these like the moving ones?
No, there are particles that are whizzing through here, but they're in equilibrium. They're whizzing through at a high speed. But what I'm drawing here are the fixed ions. And it turns out, I'll show you in a moment, it turns out that in this region, the concentration of mobile carriers is very small because they're going at very high speed. The main charge you have here in this depletion region are the fixed ions that are left behind, the nuclei of the atoms
But
that are charged.
like in the p-doped region, shouldn't be the fixed ions positive, and in the n-doped region, the fixed ions negative?
No, I don't think so. I think it's this way. Please correct me if you think I'm wrong. Yeah, what's left behind are the fixed ions, right, from both sides. This is the n-doped side and this is the p-doped side. And the electric field will point this way, right, from plus to minus. And we know the electric field always pulls carriers home. The built-in electric field that builds up between oppositely doped regions makes carriers go home. You remember that if you're ever confused about it. It pulls the holes back home to the original p-type region, and it pulls the electrons home to the n-type region. It opposes the diffusion current. Is it clear? It must. It must, because there can be no net current in the ion. Yeah, so anyway, it turns out that, magically this it's hard to think about it. You can't think about it except if you think about charge. But it builds up an electric field magically that opposes the diffusion current. And because there's an electric field, it builds up a potential difference, an electric potential difference between the two regions. You can also think of it that way. The electric potential is just the integral of the electric field, right? And so that builds up an energy barrier. There's various ways to plot it, and you should know how to plot below this thing, which I have to erase now, but I can just draw it again over here. Let's draw this p junction again. It's N, it's P, and now let's draw the charge density as a function of space, and the electric potential, which is just built up out of that, and the electric field. So we start with the charge density, then we can draw the electric field, and then we can draw the potential phi from that. Okay, what does the charge density look like? Okay, so it's plus on this side. So it's like a bump. Actually, it's a very square bump. It's like that. Positive on the left, negative on the right. Right, that's this. And then the electric field, how does that act? It's zero in the neutral, in the regions outside the space charge region, the electric field is zero. And then it starts increasing. Let's call it positive to the right. Right? It's zero at the boundary. Then it comes to the most positive value right in the middle, and then it goes back to zero. Right? It's just integrating this curve of charge, just the integral of that. And does it make sense? The biggest electric field is right in the middle, right? Where you have the most positive pushing that way and the most negative pushing in the same direction. Right in the middle is the biggest electric field. At the edges, the field is zero. Okay. And then if you integrate the electric field, you get the potential difference between the two sides. And that looks like the integral of this triangle, which is, well, I'm not going to draw this properly. It's just something that looks like two parabolas. The integral of a line is a square function. And so that builds up a voltage between these two, actually a potential between these two N and P regions. And that potential is, anybody know roughly what it is? Yeah, there's no hard rule. It depends on what the doping ratio is between the two sides. If you dope it really strong ratio, then the built-in potential will be higher. But typically it's around 0.6 volts or something. 0.6, 0.8 volts, something like that. Yeah, again, it's a huge, it's much bigger than the thermal voltage. Much bigger than KT over Q. Okay. hundreds of millivolts, not 25 millivolts. Yeah, so that's the potential barrier that electrons have to climb to get into this channel. Right, here's an N and a P, just like over there. And so you can think that potential barrier is kind of between, the electrons have to climb that because you have to do work on them to get them into the P region. Because if you push an electron this way, the electric field's always pulling it back, right? So you have to do work on it to get it into the P region. That's why it's a potential barrier. So that's also another reason why there's so few electrons here, because there's a potential barrier. Even though they're whizzing around like crazy, they have to climb this big barrier to get into the channel. Yeah.
So when you're actually connecting a diode to a voltage source, it goes P first, right? So shouldn't the potential be flipped the other way?
It's very confusing. This is the potential energy for electrons.
Okay.
Okay, it's somebody made a mistake and made electrons negative in the beginning. And that caused endless confusion since then. But it's a potential energy for electrons. You don't worry about that sign, right? If you don't get consumed by worrying about the sign here. It just means that you can think of a potential energy for electron. You have to do work on the electron to make it climb up this barrier.
I see.
Okay.
So it's net work, just in general. It's not the actual potential difference.
There is no, you can't measure this potential difference. This is another confusing. You can't stick a voltmeter on there and measure this potential difference, because when you stick the metal electrodes on there, they also have their own, junction characteristics, even though they're not junctions. So it turns out that you won't measure any voltage if you just stick a voltmeter on there. But there is an electric field in there, right? You just can't measure it by sticking a voltmeter on it. Okay, is that clear? I mean, it doesn't explain why you can't measure the voltage. And it's not like you can take this junction and just power a light bulb from it because there's a voltage across it, right? It doesn't work like that. It's just the potential only builds up to oppose this big diffusion current. So it's in equilibrium. Okay. I hope that's helpful. The end result is that there's a potential barrier that makes it hard for electrons to get into this channel. And to get them into the channel, you have to make it easier. How do you make it easier? Really simple. You just put positive charge on the gate. That attracts the electrons into the channel, or another way to think about it is it lowers the energy barrier. It makes it easier for electrons to get in the channel. And that's why current starts to flow between the two sides. It's clear, right?
Quick question.
That's for an NFET. Okay, yeah.
Sorry, the feed-up region and the channel, is it the same place or is it a different place? What is the channel and what's
The channel is
on top?
the region right at the surface, right below the gate. This is an insulator here, right? That's gate oxide, silicon dioxide. Has a band gap of about 8 electron volts, huge band gap. But right below that, the channel is two-dimensional, almost two-dimensional plane right at the surface between the source and drain.
Okay, basically the surface of the feed-up region is the
Yeah, right at the surface of the silicon, right at the boundary of the silicon dioxide, the insulator. That's good. Thank you for asking this question. It's really, really useful. No such thing as a dumb question. Okay. Let's see now. Okay, now, do you want me to write the transistor equations first and then we'll reason through why they happen? Maybe I'll just summarize the transistor equations about threshold, and then it'll be quite clear. I can explain them in a few minutes how the equations come about, right? And then we'll look at it more carefully. By the way, these are the only equations you would ever use for hand calculation. They're really simple. Forget about all quadratic forms and all that. You'll never use them. Not once in my life have I used any fancy forms. Okay, so I'm going to give the ones that are actually useful for hand calculation and understanding and stuff like that. Anything past that, you're going to use some simulator, right? To order all these second order effects and stuff. So we're just going to write the transistor symbol. Then I'll talk about the PFET later. There's many ways to draw this transistor symbol too. Like this is an NFET. One more, it's like this PFET symbol. There's a bubble here. That means it's a PFET, right? Because there's a hole instead of electron. I personally like Andre von Scheick style, where you just draw like this. You don't even bother with the squiggles faster. Yeah, this means ground, and this means VDD, power supply. It's clear, right? That's a symbol for this cross-section thing up there, where this is the gate. Which is the source end of this NFET, the bottom of the top? Where do the electrons come from? Bottom, right? Okay, so this is the source, and they fall out of the drain. And now for the PFET, this is the gate. Where do the holes come from? This is simpler, right? Holes go from high voltage to low voltage, right? Because they're positive charge. So it's really easy. The source is always the higher voltage. It's easier because they're positive, right? They fall from high voltage to low voltage in the direction of the electric field. Okay. But you know, everything I tell you about NFETs applies for PFETs, except that the voltages are flipped, right? To turn on this PFET, you have to attract holes into the channel. How do you do that? By putting negative charge on the gate, making the gate more negative. That makes it easier for positive holes to get into the channel. Is it clear? And then the voltage that matters is this side, right? This is just where they fall out. It's like the bottom of the waterfall. You know, if you think about it, this is really a useful analogy. Think of a dam, and only it's a foggy night, so there's a lot of mist over the water. And then there's the dam, which is holding back the mist. The mist is like this cloud of electrons, right? It doesn't matter how high the dam is. It only matters how close the water is to the top of the dam. As long as if the dam is high enough, it doesn't change the current, right? Once you go past a certain point, the current won't change. It only matters how close the water is to the top of the dam. The bottom side, the drain side, doesn't matter as long as it's high enough. Just like that. As long as the drain to source voltage is big enough, the current's not affected by the drain voltage because the electrons just fall out. Okay? It's only when the voltage is small that this voltage matters. The voltage difference is small. So I'm going to write the drain source current above threshold. I need to explain what that means. And in super, we call it super threshold to oppose it for subthreshold, but other people call it strong above threshold or strong inversion. I'll explain what that means too. And it's the drain source current as a function of the gate voltage. So there's two conditions where a small VDS, small drain source voltage, and big drain source voltage. Okay. Okay, so let's reason about what the current is above. Okay, so I need to explain what this strong inversion means. Okay, so if you just build the transistor and put all 0 voltages in all the terminals, then this will really be P doped here. It'll really be P type, right? If you put a little bit of positive charge on the gate, which is a metal, it's very highly doped silicon, so it just acts like a metal. So you're just putting positive charge, you just put a little bit on there, and the effect of that is just to push away these holes. They just get pushed away from the surface, and then you end up with the bare ions, and of course there's a field line connecting each one, right? You can think of this field lines, these field lines. So the first thing that happens is you push away these mobile holes, and you basically made it like the space charge region. Right? It's just fixed negative ions, and you've depleted it. Why have you depleted it? Because it started out P-type, and you've gotten rid of the P's by pushing them away, the holes, you push them away, and so now it's depleted. Okay, so there's just these fixed ions. Okay, that's the first region, and that's the subthreshold region of operation. But then, actually what's happening at that point is vapor starting to rush in from the source end. The source is it's easier to rush from the source because the potential barrier is lower, right? Usually the drain's at a high voltage, so there's a huge potential barrier. So at the source, things are starting to rush in exponentially, just like vapor would start to go over the dam. It's actually, the process is exponential because of the way the energy is distributed, but it's still a tiny fraction of this fixed charge. Okay, so it's still dominated by these fixed ions. The charge density here is just these fixed ions. There's a little bit of mobile charge, exponentially increasing as you increase the gate voltage or decrease the source voltage, but it's still small compared to the fixed charge. However, at a certain point, it's like the dam, the water level reaches the level of the dam, right? And suddenly water starts rushing over. And what happens is now, at a certain point, it becomes energetically easier to just not push away this charge, but instead actually induce mobile electrons at the surface. So every time you put another charge on here, you actually get a mobile electron. Comes from the source. That's the strong inversion region. So every charge you put on the gate is balanced by a mobile electron that came from the source. And that's the region I'm talking about here. It's not a vapor of electrons, it's really a sheet of a charge, a macroscopic sheet of charge, which has a higher density than this doping density. That's kind of the threshold amount. Okay, at that point, you have a sheet of charge in the channel, which is proportional to the gate voltage minus this threshold voltage. And so then the current flowing in the transistor is proportional to the electric field across the transistor. That's the VDS divided by L. That's the voltage divided by the length times the charge density. What's the charge density? It's the gate source voltage minus this magic threshold voltage. Yeah. And then the current is also proportional to the width of the transistor and the mobility and the oxide capacitance. Because the bigger the oxide capacitance, the more charge you get per unit voltage, right? The definition of capacitance is that the charge is equal to CV, right? So let me try to explain where this equation comes from. This is what happens for small drain source voltage. This is the electric field component. And this stuff here is the charge density, right? So this is the drift current caused by the electric field between drain and source. Okay, and what is this W here? That's the width of the transistor into the blackboard. The wider the transistor is, of course, the more current you get. Okay, and the mobility here is just how fast the charge moves in response to the electric field. Okay, so that's the whole above threshold equation, which is a consequence of the drift current acting on the charge in the channel caused by going above threshold a certain amount. Okay, to understand this, I'm going to draw another curve here because it might be helpful. It's a nice curve that shows as a function of the gate voltage or the gate source voltage. Why do I say gate source voltage here? It's because in a transistor like this, it doesn't matter what the gate voltage is relative to the substrate so much as it matters relative to the source, because the source is where the carriers are coming from. They're not coming from the substrate, right? So it's the gate to source voltage that's important. Okay, so I need to draw the curve here. So this is a curve that I'm going to plot. On this axis here, I'll plot the charge density in the channel. Charge density. Call that Q inversion. That's the inversion charge per unit area in the channel. And on this axis, I'll plot the something you'll see a lot next week, which is the surface potential, psi S. Let me explain what that is. Let's call this ground here. And psi S is the potential right there at the source end of the channel. That's so-called surface potential. In the same way that I mentioned there's a potential here, this one, it's kind of like the energy level at the channel end. Okay. Okay, so what do you think those two curves look like as a function of this gate source voltage? Given that I just wrote this equation here. So what I said was that the mobile charge density is essentially zero when you're below the threshold voltage. So therefore this mobile charge density should be zero. Actually, it's increasing exponentially, but for the purpose of above threshold, it's zero. And then as you go above threshold, the charge density just increases linearly. Okay, and so this voltage right here is the so-called magic threshold voltage. Threshold voltage is around 0.5 volts, 0.8 volts, around a fraction of a volt, several hundred millivolts. Okay, so that's what the mobile charge density, it's zero for the purpose of this equation. When you're below threshold, there's no mobile charge in the channel. And when you go above threshold, the charge density in the channel just increases linearly with the voltage above threshold. Yeah.
The threshold voltage you're mentioning is the property of the material that you're using. Is a property of the material that you're using, right? So
The question is that a property of the material? Yeah, is the threshold voltage a property of the material?
yes.
Yeah, exactly. It's a property of how much you've doped the channel relative to the source. And people actually insert in this channel, they do what they call a threshold adjust implant. They dope they grow the N and P wells. This whole thing is sitting in a P well. It's just a bulk region. And after that, they always implant a thin layer of donors or acceptors here, boron or phosphorus, something very, very lightly implanted, like maybe a few kilo electron volts. It's right at the surface. And that's designed to adjust the threshold voltage so that the N and P FET thresholds are roughly equal. You want, for logic circuits, you want the N and P FET thresholds to be about the same. So they always do this little implant of a certain amount of donor and acceptor just to adjust the threshold to the good level for logic circuits. Is it clear? Okay. Okay, so that's what the charge density looks like. It's a function of the gate source voltage. Now, what does the potential look like? Giacomo will talk about this again last time, but basically what happens is as you increase the gate voltage, the surface potential will increase linearly. I have to draw it properly here. It actually increases with a slope less than 1. You'll hear all about this cap on that next time. And then as you go above threshold, charge is rushing in from the source. And so what happens is the surface potential gets so-called pinned, gets stuck down. And so then it only increases logarithmically, very slowly. It's pinned. And that's because charge is rushing in. And but below threshold, because of the capacitive divider that Giacomo will tell you all about, the surface potential increases like slope of like 0.8, 0.7, 0.8, something like that. In other words, the voltage, the potential here at this end of the channel only increases 0.8 as much as the gate voltage changes. That's because there's another capacitor here on the bottom side that's pulling the voltage down. So it's actually a chain of 2 capacitors, right? There's one for the oxide, and there's another one for the so-called depletion capacitor. This oxide capacitor is this one, that's COx. And there's another one formed by the space charge region, that's a CDEP. It's actually a distributed capacitor. It's formed by the distributed charge in the space charge region. And these 2 capacitors together control the surface potential. And so this is a series of 2 capacitors. You're in control of the gate voltage, but what actually matters for the transistor operation is the surface potential here. And that's also controlled by the capacitor from the bottom side, which is the bulk. You'll hear more about that next time. That's why, and Giacomo will show you this next time, if you look at the surface potential as a function of the gate source voltage, it only increases with like a slope of 0.7, 0.8. Right, and then once charge starts rushing in, the surface potential becomes pinned. And now what happens is the charge density, the sheet of charge just increases linearly with the voltage. And that's why you get this particular equation for small drain source voltage. Okay. Okay, so now what happens when you have a big source drain voltage? I'll just write the equation first. Let me hamper by the fact there's no good eraser. Try to do this here. The problem is that now it's wet. So I have to wait for it to dry out a little bit. I'm going to now show you something quite interesting. When you make a big drain source voltage, instead of going linearly with the gate source voltage, the current actually goes as a square of the gate source voltage. And it's not why you think it is. It's not because it increases faster or something. It's sort of non-intuitive at first, but the equation is very simple. I'll first write the simple form of this equation. That is simplified as beta V overdrive times VDS. I'll write that again. And V over, it's the overdrive voltage. Why is it called overdrive voltage? Because it's the amount the gate source voltage is above this threshold voltage. Okay. So you can see the equation for small VDS is really simple. It's just a constant beta, right, which is mu Cox W over L times the overdrive times the drain source voltage. Nice simple equation. That's the first thing you're going to measure. Okay. You're going to set a small drain source voltage, I think. Is that right, Junren? Is that the first measurement? The small VDS drain current.
Yes.
Yeah. So you're going to set a small drain source voltage on your end fit and sweep the gate voltage and just measure this. And what you should get is exactly that curve, right? In fact, let's plot it over here. Now we're plotting the linear drain source current versus the linear gate source voltage. And what you should see is that actually you're going to measure a current below the threshold voltage, right? That's the reconversion current. And once you go above threshold, if you plot on a linear scale properly, you should see something like this. It should be linear in the gate source voltage, or small VDS. The slope of that should be exactly beta, which should equal mu times Cox, the oxide capacitance per unit area, times the W over L of the transistor. Okay, let me ask you a question. Where is this L? What is this L coming from? Yeah. That's the length of the transistor, right? The L is just this length here. That's equal to L. And the width is going into the board, right? W is how wide it is in that direction. Okay, but what's the reason there's a 1 over L there? Why is there a 1 over L here? Remember, it's VDS divided by L. It's a voltage divided by distance equal to electric field, right? That's why there's a 1 over L. The bigger the electric field, the bigger the current, right? Okay, this is drift current. Okay, that's the first experiment. Okay, but now when you go above threshold, big VDS, you go past saturation, then it becomes just beta over 2 V overdrive squared. Just goes as a square of the overdrive. And so that means if you go above threshold, or make another plot over here. Sorry if my plots are so messy, but it is organized up here. Okay, so above threshold, so this is a small VDS or let's see, this is, by the way, this is called small VDS. I need to call it, this is called the ohmic region. Ohmic or linear region. And this is big VDS is called saturation region. Saturation, because when something is saturated, it doesn't increase more. It's full, somehow full. But the air gets saturated with water vapor. Here, the transistor current doesn't increase when you increase the drain source voltage. In this saturation region, you're going to plot the square root of I, VDS, versus VGS. And then you should again get a line, right? If you plot the square root of the square, yeah, it should also just be a line. Right? And then from the slope of this line, you can measure the square root of beta or something. You can work it out. Is it clear? If you take this equation and take the square root of it, that's the current. If it goes like the square of the overdrive, then it should be a straight line if you plot the square root of the current. You know, every time you should always make things that look like lines if possible. Then you can see non-ideality if it doesn't look like a line. Your eye is very good at seeing when things are not aligned, right? So always plot things as aligned. Same thing we're going to do next time when you plot the current versus VGS for smaller VGS, where the current should be exponential. Then you should plot it as a log plot, right? Because then if it's really exponential, it'll just be a straight line on a log plot. Yeah. Yeah, but now, why does it go? Now I need to erase a board here to talk about this business. This is going to be a little hard to explain. Okay. In certain way, it's very easy, but you might have a hard time getting it at first. I'm going to have to erase this board. Is that okay? And think of your questions right now so I can attempt to answer. Are there any questions about anything here?
Sorry?
Yeah.
Why is the mobility and the capacitance are constant
The question is, why is the mobility?
and the capacitance in the for the linear region?
Yeah, why does that equation have mobility and capacitance?
No, why mobility and capacitance coefficient constant?
Oh, it's not really constant. The capacitance is constant because it's just the gate oxide capacitance, which is on the order of a pico, let's see, around a picofarad per square micron.
The mobility have a relation to the voltage, right? So
Yeah, in reality, the drift current, I've written it like this, that the drift current is proportional to this electric field and a constant mobility. It's not true. For a very large electric field, it's not linear anymore because the carriers get accelerated a lot between collisions, and eventually there's so-called saturation velocity. No matter how big electric field you put on, it doesn't go faster, right? And actually, that's true for a lot of digital transistors now. The current is not proportional to electric field anymore. It just becomes constant with electric field. So, but this assumes for small electric field that the drift current is just proportional to electric field. Is that what you're asking?
That we only consider under the assumption that in small electric.
Yeah, just a small electric field. Anyway, that's what you've assumed here, right? Small VDS.
Where does the U come from again?
Mu, not U, mu, mu, that's the mobility. That's just a constant, has to do with the semiconductor material. It's how fast the charge moves with electric field. It has units of centimeter square per volt second. Don't worry about the units. I mean, there's, by the way, and this constant here, the diffusion constant, is just another constant. Actually, it was Albert Einstein who showed, and this is what he was, I think one of the things that he was credited by, he got the Nobel Prize. He showed that the drift and diffusion constants are related to each other. In fact, they're proportional to each other just by kT over Q. In fact, the diffusion constant is just kT over Q times the mobility. Why is that? Why should diffusion constant depend on temperature but not mobility? It's very obvious why that is, right? Diffusion increases with temperature, right? Because the hotter it is, the faster things move around. Of course, that doesn't affect how the carrier is moving to first order, due to electric field, right? And so that's why the diffusion is, I mean, you never actually use this. It's just to be aware that diffusion is proportional to temperature, absolute temperature, somehow, and mobility is not. But both are a function of temperature. It gets complicated how mobility depends on temperature because it depends how the crystal lattice vibrates and phonons and all kinds of complicated stuff. You don't need to worry about it. You can't control them anyway. It's just something you get when you fabricate the chip. Yeah. Any other questions here?
So the surface potential is uniform along the channel, or?
Yeah, under these conditions, that's a very good question. Do we assume a constant charge density in the channel under these conditions? Yes, because there's only a very small electric field across the channel, then the charge density is just constant in the channel. It's just a uniform sheet of charge. Yeah, under these conditions, a small VDS. Under ohmic or linear region. Why is it called ohmic or linear? Because the current is proportional to the voltage from drain to source. It's like a resistor. Yeah. Is that helpful? Okay. But then, as I said, as you increase the gate voltage, the current, well, let's make it really simple. Yeah, another question?
Just wanted to ask about that C, because I didn't get that.
The Cox here?
Yeah.
The Cox is the oxide capacitance. So the charge density in the channel is C divided is CV. Q equals CV. You know that, right? Q equals C times V. Yeah, that's what it's from.
You told that the electrons that came from the end of region, right?
Come from the source.
of the source, but aren't they like you also have like a MOS capacitor?
This is a MOS capacitor, yeah, but
Yeah, but without the sources, and then there's also inversion.
you can, if I didn't have a source drain here and I just built a gate over a P-type substrate, I would have a MOS capacitor. That's correct. And I could induce a depletion region. And if I increase the voltage a lot and waited a long time or shine light on it, then I would eventually get mobile electrons. But normally you wouldn't have any place to get mobile electrons because there are no mobile electrons.
No, but it's because it's like the band gap is like the gets banded, right?
I'm trying to avoid the band gap and the band diagram. Yeah, it's very confusing for beginners, these band diagrams. Yeah, forget about the band diagram. Band diagrams are actually quite useful, but we don't need to know about them now. All it did, I remember when I learned about it, it was, it's very confusing, this band diagram. You say, well, what's the point of this band diagram? Eventually it becomes useful, but it's not useful for learning it initially. Trust me, I thought they were awful, these band diagrams. In fact, Yanis Tsividis, do you know Yanis Tsividis, the guy who wrote the book on the MOS transistor? He wrote the entire book without once using a band diagram because he didn't like him either. He managed to write the entire book without one band diagram, even though they're critical to understand semiconductors. Anyway, you don't need to know about it, right? This band diagram. You do need to know that there's a potential barrier between N and P. That's important. And that you can modify the potential barrier by changing the gate voltage. But your question was related to this MOS capacitor. Yes, you're right. This is a MOS, metal oxide semiconductor capacitor, right? One plate of the capacitor is the gate. The other plate is this depletion capacitor or this layer of inversion charge, one or the other. But you do need a source drain there to get the charge from if you're going to invert the surface. If you just make a MOS capacitor and don't have an end source drain, or you don't actually need the drain, right? You just need a source of electrons somewhere. If you don't have that, all you're going to get is a big depletion region at high frequency, right? It's just going to push away the holes and let them come back. But you won't get electrons. Eventually you would get them, right? Just because they get thermally excited, or if you shine light on it, eventually you would get some electrons, but there's no electrons here, right? So the way you get the electrons quickly is from the source. Yeah. Yes. So you need that. If you're going to make a MOS capacitor, you need that source there. Otherwise it won't work very well, or it'll be very, very slow. It's good questions. Thank you for asking. Okay, now I can erase this.
Also the both two equations.
Before I go into trying to explain why the current goes like the square of the gate voltage when you go above threshold, when you saturate the transistor, when you put a big voltage across the drain source.
So what do we have?
Why is the overload multiplying?
Overdrive. Yeah, not overflow, overdrive.
Why is it multiplied with and not added to the voltage, for instance?
For this equation here.
Yeah.
Yeah. This beta times the overdrive is the charge density. Sets the charge density in the channel.
Yes.
It's this yellow curve. And the VDS sets the electric field across the channel.
Okay.
The charge density times the electric field is the drift current.
Ah. Okay.
Yeah. Is it clear?
Yeah.
Okay, that's good. Thank you for asking that. So this part here is the QI, and this part here is the electric field. So the product of those two is the drift current, which is the current. Okay. Okay, so now let's try to understand this this saturation of strong inversion or super threshold or strong inversion. Okay, so I say it's beta over 2 V overdrive squared. Let's write it out properly as VS minus V2 squared. Okay, it's the same thing. Okay, what does it take that for? Okay, so now I'm going to try to explain it here in terms of the levels of voltage on the gate, source, and drain. Okay, so here's the source voltage, here's the gate voltage, here's the drain voltage. Sorry, it's not correct. No, the drain voltage is higher than the source voltage.
Can you hear us?
It's an NFET.
No.
Well, I won't draw the drain voltage yet. I want to draw just the source of air voltage. Okay, and now there's a certain threshold voltage. Let me draw that in another color. That's VT. Okay. And where's the overdrive in this picture? It's VG minus VT, right? So this is the overdrive. Is it clear? This is a picture of voltage. Okay, so I was just talking about the source and the gate. And the gate, by definition, because you're running above threshold, the gate is above the threshold voltage by this amount. The overdrive. Okay. Now the drain is at some other voltage. Okay. It's higher than the source. It can be any voltage you want, right? But I'm going to ask you a question. What voltage does the drain need to be at so that the drain is right at the threshold voltage? That the drain gate voltage is the threshold voltage. In other words, I'm asking you a question here. What VD do you need here so that this gate to drain voltage is exactly the threshold voltage? It's exactly the overdrive, right? If I put the drain at the overdrive voltage, then this voltage is what? Is going to be what? Isn't it going to be VT? Right? Because this voltage is VT plus the overdrive. That's VT plus the overdrive is that voltage. Here it's VT plus the overdrive. So when the drain gets to the overdrive voltage, then the drain is at the threshold voltage. In other words, it's right at threshold. Okay, once the drain gets above this voltage level, the current doesn't increase anymore. Why? Because the drain barrier is high enough that it doesn't have any effect anymore. So at that particular overdrive voltage, the transistor current saturates, and it doesn't increase with drain voltage much anymore. And so I need to draw a curve. Let me draw now the curve of, before I draw the drain current versus gate voltage. Now I'm going to draw the drain current on a linear scale versus the drain source voltage. It's clear, it's a different curve, right? This is the drain saturation curve. It's how much the drain current changes with drain source voltage. Okay, how much does it change with drain source voltage when the drain source voltage is small? That's the equation we drew before, it's the ohmic region, right? So it'll go like this. Okay. Now, when we reach this overdrive voltage, this is if it's set by the thing, then the current won't increase anymore. It will saturate. That's what happens. This is the ohmic region. And or linear. This is the saturation region. That's for one particular gate voltage. If I increase the gate voltage, what happens? Now we get a different curve, right? And we get a steeper curve. But to increase the, if I want to increase the current, I have to increase the overdrive, right? I have to increase the gate voltage. So the overdrive is going to be a little bit higher. So now the current will increase more, but it'll also saturate a little bit later. Because it'll take more drain voltage so that the drain goes out of strong inversion. See, it seems to be very hard for people to get this. Basically, the overdrive sets the saturation voltage because at that overdrive voltage, the drain goes out of inversion, goes into weak inversion. This is not the way it's traditionally taught. You guys have all been taught about pinch off and stuff like that. I don't think that's one way to look at it, but I think it's a simpler way to look at it, right? At this overdrive voltage, which is set by VGS, the drain current will stop increasing. Okay. Okay, but now we can write we can just take the ohmic current and just replace it with this drain source voltage. So if I take the ohmic current, IDS with beta times V overdrive times VDS, and swap in the fact that this this current will saturate when VDS is bigger than the overdrive. What do you get? If I substitute in here the overdrive, what do you get? Because that's where it saturates. You get beta times VDS squared, right? Times the overdrive squared. Is it clear? That's where the square behavior comes from. But you have to put in a factor of 2. If you're working on in detail, you know, it starts curving over. So it's not, it's a half of what you think it would be. That's the intuition about why the current goes as a square of the overdrive voltage above threshold. One factor is just from the charge density in the channel, and the other factor is from that at that particular drain source voltage, which is equal to the overdrive, the current saturates. Okay, I hope you let that sink in, because you'll never forget it once you understand it this way.
So where is the coefficient over 2 come?
You guys can't see it, but yeah.
So where is that coefficient over 2 come from? Because intuitively.
Where does this equation come from?
No, the coefficient over 2. Because
You can work it out in detail. It's not exactly 2 anyway, right? There's a kappa in there and stuff like that. Listen to the lecture and watch this detailed calculation. You know, you see a calculation, which I'm not going to bother to show you, where you compute the square of the charge density at each end and the integrated stuff. You won't remember it anyway. You have to watch it and do it for yourself, this more detailed calculation where this factor of 2 comes out. But you can kind of imagine, just if you want to remember it intuitively, if you just extrapolated it, you wouldn't get this factor of 2, but it actually bends over. And it turns out that it's a factor of 2. Don't worry about the details of that, right? I could do the calculation here for you, but you'd forget it as soon as you saw it. So it's better you watch it, or better still reproduce it for yourself, because it's a cool calculation. You get the full equation of the above threshold transistor, including drain source voltage, all that stuff if you go through it more carefully. But it's pointless to show it to you, because it'll go in one ear and out the other. But it's better you watch it, like I say, and then work it out for yourself. And if you have questions, then you can ask questions about some steps of that calculation. Okay, but it boils down to this. It's the only one you'll ever use, either this one or the other one. You know, in the hand calculation. Okay, now, okay, yeah, I have to tell you about one more very important thing. I want to take a short break, though. 5 minutes.
Could you further explain, like physically you went before, that when it saturates, it's because
The drain goes out of inversion.
What does this mean?
Right, the drain goes into weak inversion. It's not inverted anymore. Okay, you understand that the channel is inverted here, right? Here, the gate is above the threshold voltage, so you have a sheet of charge here at the channel. Right? That's because the gate is above the critical voltage, the threshold voltage, and now the charge rushes in here. Where is that charge coming from? It's coming from the source, right? Okay, at the drain end, if you raise the drain voltage up to a certain voltage, it won't be inverted anymore. You know, if this voltage is very small, you won't be able to get charge from the energy barrier from the drain end will be too high, and it won't be inverted anymore. It'll pinch off, if you want to call it that. So you'll have you won't have sufficient voltage between the gate and drain to invert the surface at the drain end, and that happens exactly at this overdrive voltage. That's why it saturates at that voltage. See, the bigger the gate source voltage is, the bigger the voltage that you saturate at. That's what happens above threshold, right? So if you put a big gate source voltage, like 4 volts, right? Then the overdrive is going to be like 3 volts. The transistor will be linear for like 3 volts above the drain source voltage. Right? In subthreshold, it all happens within 100 millivolts or so. It's a different mechanism, right? Giacomo will show you next week. But above threshold, the harder you turn on the transistor, the longer the region that is linear. Yeah. But I have to explain you one more thing, which is drain conductance, because you're also going to measure drain conductance. This is important that you see this, but you need to have a mental break of 5 minutes. Okay. So what I haven't talked about is what happens out in the saturation region. And that's an extremely important region of operation of the transistor because most amplifiers you build, the drain is going to be saturated. And the current should not change with voltage, with drain voltage, but it does. If you actually measure a transistor, this curve, the slope of this curve here, which I'll draw it in reality. Let me draw it. The actual curve is more like this. It's going to have some finite slope to it. It might be complicated. It might curve up a bit and stuff. You know, it's an idealization that it's just a straight line, but it's a pretty good idealization. Anyway, the slope of that curve, which is this slope here, is the drain conductance, GD. We use G for conductance and D for drain conductance. There is a finite drain conductance. It's like a resistance of the drain. And I want to, just to understand where that comes from and how you're going to measure it and how it scales when you change the transistor length. Okay, so what do you think this drain conductance comes from? Let's draw the cross section of, for reference, I'll just draw the cross section of the transistor down here again, so we can speak about it a bit. Let's draw green for the source. And by the way, you know why they use red for poly? Because when you look in a microscope, the polysilicon actually looks red. Somehow the polysilicon actually appears to be red. That's why they always draw red. And green, the active region kind of looks greenish if you look at it in the microscope. This is called active region of these doped regions for source drain. Okay. So why do you think that the drain current increases when you increase the drain voltage, as I've drawn up there? Why do you think there's a drain conductance? What's the first guess about that? I mean, that's not a resistor, right? Well, it is a resistance. There is kind of a resistance going along the channel, but that's not why this happens. In fact, if so there's, do you remember these depletion regions, these space short regions you have between every p-n junction? So actually there's a depletion region around this n regions here to this p region. I can draw this little depletion region, just draw it like this. It's actually a two-sided depletion region. And when you operate the transistor, of course, there's going to be a depletion region in the channel. There's going to be a depletion region around the drain. And it's a double-sided depletion region. Remember, you have the space charge region where it's positive on one side and negative on the other. Anyway, it's a space charge region where there's no mobile charge, just fixed ions. So, but what happens when you increase the drain voltage? That's what we're talking about, right? Here you're increasing the drain voltage and the current is changing. What do you think happens to this depletion region here?
Making it bigger.
Gets bigger, right? The bigger the voltage you put across a p-n junction to reverse bias it, the wider the depletion region. It must be so because as you apply more voltage, that voltage appears across the depletion capacitor. And to get more voltage, you need more charge. And the only way you can get more charge is making the depletion region wider. So if I have two voltages and I increase the drain voltage, I say I make it, take another color blue here, I'll make the voltage higher, right? Make VD a little bit higher. What happens to the depletion region? Well, nothing happens over here, right? Nothing much happens here. But what happens is the depletion region around the drain gets a little longer, a little wider. And what does that do to the transistor length? It makes the transistor length shorter, right? So the L is actually decreased a little bit and making the drain voltage higher. And do you remember this factor of 1 over L? Yeah, the shorter the transistor, the bigger the electric field. Or in subthreshold, as you'll see next week, the shorter the transistor, the bigger the concentration gradient, right? Because you have the same concentration ratio, but shorter length. It's going to make a higher gradient. Either effect here, either increasing the electric field or increasing concentration gradient, both increase the current. And so that's why there's a slope on this curve. It's called the, this is called drain conductance. I'll write that. I'll write it. And also called, it's also called early effect. Okay. It's not early because it's like early in the day or something. There was a guy named Jim Early. There's a guy named Jim Early who observed this in bipolar transistors. His family name was actually Early. That's why it's called the Early effect. In bulk PNP bulk transistors, same effect happens at the base that changes as a voltage. The applied reverse voltage. Yeah, so this early effect is caused by the transistor channel getting shorter. Since it's a geometrical effect like that, it actually has really interesting behavior. That if you now plot this early voltage, well, it's the early effect, but if you plot it, you'll take one transistor saturation curve, let's exaggerate it. Actually, it's not exaggerated. If you make a really short transistor, you can have a considerable slope on it. And then you extrapolate it out here. Intercepts the axis at this early voltage called VE. Yeah, that's just this curve, it's saturated. And what's this intercept right here? That's called the saturation current, ID sat. And what's the conductance of this slope here? DD. That's just ID sat divided by VE. Okay, so GD is just the saturation current divided by the early voltage. Now, if I increase the gate voltage, I'm going to get a different curve, right? But because this early effect is just a geometrical effect on the transistor, what happens is that if I increase the current, all I have to do is draw a line like that. And then actually the curve gets steeper, right? So it intercepts at roughly the same place. If I make the current smaller, by decreasing the gate voltage, then it actually gets flatter. I mean, I'm not doing it properly. It should actually have a slope like it. It should actually have a slope like that. You see from this that this drain conductance is proportional to the saturation current. It's not a constant conductance. It's actually proportional to the current. The typical value of this early voltage, I mean, it's an approximation. First of all, it's an approximation to say that this early voltage, this intercept point doesn't move around. It does move around a bit. It's a complicated three-dimensional physics that's happening here with this draining out. The fields, the depletion region has a funny shape, and it depends on why the transistor is complicated. But you can approximate and say, look, it's roughly an early voltage, the intercept, minus early voltage. And the typical value of this early voltage is going to range from like maybe 1 volt up to 100 volts, depending on how long the transistor is. Okay, you need to understand, why is it proportional to the length of the transistor? Actually, the early voltage here, the longer you make the transistor, the bigger the early voltage. In other words, the longer you make the transistor, the flatter the curve is, right? Because the big early voltage means that the curve out here is going to be flatter and flatter. That means it's going to be less conductive. The current's going to change less when you change the drain voltage. That's what you generally want it to be, a stiff current source. You want to be in control of the current to make an amplifier. So why is this early voltage proportional to the transistor length? Well, is it? Yeah.
Yeah, the depletion regions bit in comparison to the.
Exactly, you exactly got it. It's because the depletion region doesn't depend on the transistor length. So the depletion region variation as a function of the transistor length decreases as you make the transistor longer. If you make a really long transistor, then this little bit of depletion region variation becomes a tiny fraction of the whole length. If you make the transistor really short, this depletion region variation makes the transistor channel length change a lot, right? So is it kind of obvious? The longer you make the transistor, the less the effect of this depletion region variation, right? So generally, VE is going to be approximately proportional to the transistor length. Maybe you can approximate it and say it's like 10 volts per micron. I mean, that's just a very rough approximation. You get 10 volts. Don't quote me on that, right? But you get like 10 volts of early voltage per micron of transistor length on an order of scale. Could be 1 volt, could be 100, depending on the process. So just that's the way this drain conductance effect works. And it's a really cool effect. You have now enough information from what I've shown you to compute what's called the intrinsic transistor gain. How much voltage gain can you get out of one transistor? Shall we just finish with that? Let's do it as an exercise. You might not get this the first time, it might be too much for you. It's a cool dimensionless number. So let's take a transistor, a simple transistor circuit, and end that going into a perfect current source. This current doesn't change with the voltage here at all. This is the input voltage, and here's the output voltage of this amplifier. This is ground, and this is positive supply. And now I set up this current source at some level, who knows what, 1 microamp. Now I adjust the gate voltage, and at a certain point, the saturation current of this transistor will be about 1 microamp. Okay, when the saturation current is bigger than a microamp, the voltage will go to ground. If it's less than a microamp, the voltage will go to VDD. Is it clear? All right, in other words, there'll be a certain small region of gate voltage here where the current wants to sink about what you're sourcing here. Yeah, that's where all the action happens. So if you plot the as a function of this gate voltage, this drain voltage, what will you get? Well, for small gate voltage, this will be turned off. Right, the guy will pull the voltage up. Right, for small gate voltage, you'll go up to VDD, and then at a certain critical gate voltage, it'll go down rapidly. And once you're above some gate voltage, the drain voltage will just desaturate and you'll go almost to ground. So that will be the output voltage of this circuit, and this will be the whatever gate voltage you need, so that it'll roughly equal the input. Is it clear? This is what will happen?
Can you explain the whole circuit again?
Yeah. So I take a perfect current source, ideal current source. The current doesn't change with voltage on this drain voltage. It's like your Keithley, right? It's designed to have very constant current. And now I put a transistor on the bottom of it, right? So the situation is, if this current is bigger than this current, this voltage will just go up until this thing turns off. Okay, this thing will eventually turn off when the voltage here gets to be 0, very close to 0. Right. If this current is bigger than this current, what happens to this voltage? It must go up, right? I mean, more charge is getting put in than it's getting taken out, so the voltage must go up. On the other hand, if this current is bigger than this current source, then charge is getting pulled out, and it must go down until this transistor turns off. Eventually, this transistor will turn off, right? When the VDS gets small enough, it won't conduct any more current. So you'll have two kind of current sources, a current source fighting with a current sink. Every amplifier is like that. Two current sources are fighting it out for the output voltage. And what do I mean by current source? It means the current doesn't change with the voltage very much. It's a stiff current source like this. Here, the current doesn't change much with voltage. Okay? That's how you make an output voltage amplifier, by fighting two of those against each other. Yeah, so, but there'll be a critical region in here, exactly this region, where the saturation of current through the transistor is approximately equal to the source current, where you'll be sweeping along this drain curve. And then the slope here will be determined by the drain conductance and the gate transconductance. Let me draw the equivalent circuit, and then perhaps that'll make it more clear. We can now draw exactly the same circuit as this, but here we're going to approximate. We have a current source, that's the ideal current source. Now we have the ideal current sink. That's the transistor saturation without drain conductance. And then parallel with that, we have the drain conductance. That's the GD. Okay, so this current sink right here is like this part of this curve. Except it's not even this, it's just a perfect line of current like this. Okay, and the GD part is the green part. That's this part here. Is it clear? That's the equivalent circuit. This is like the perfect current transistor saturation. This is with the drain conductance in parallel with it. Okay, so that's the equivalent circuit. And this current here is exactly given by the above threshold beta over 2 times the overdrive square. And this drain conductance is given by what? It's just this current. SAP. I just told you what it was before, right? The drain conductance is what? It's a conductance is always a current divided by voltage, right? So it's equal to ID SAP divided by the current. That thing up there. Okay, so now we can compute the voltage gain of this. We say, look, if I increase this gate voltage here a little bit, increase this overdrive just a little bit, then that's going to increase this current. But the current coming in is constant, right? So if this current here goes up, this current must go down, right? So the voltage here must go down so that this current decreases, because it always has to equal this current instead of state, right? So now you can compute the voltage gain in one line, literally one line. You just say that the change in the change in the current here has to equal the change in the current here. When you make a small change, in the gate voltage that changes this current, you have to, as a result, in a current here, the current, what's the current here? Right? Basically flowing through this conductance. It's just VD divided by, it's just GD times VD, right? The conductance times the voltage. Okay, and what's the current quote here? It's a small change of this voltage, right? So you have to compute the GM, which is G ID sat. It's called the transconductance, G ID sat VG. And you have to compute the derivative of this with respect to VG, right? It's just using the chain rule. It's just beta. The 2 comes out. It's beta times the overdrive. If you differentiate that with respect to overdrive, that's the transconductance. Now, if you express this in terms of current, I mean, this has the gate voltage and this has the drain voltage, but you can now work out what the voltage gain is exactly of this circuit in literally one line. I'll leave that for you guys to play with. You'll see it in the lecture also, recorded. But then you can find out that above threshold, you can get easily, given a reasonable early voltage and beta and stuff like that, it's easy to get a voltage gain of like 100. You know, putting in reasonable values, you can easily get like a voltage gain 100 amplifier out of one transistor. That's enough for today. Plenty. Good luck with your measurements. So you're going to measure this 3 conditions, right? Small VDS, big VDS, and early voltage. Drain conductance. So if you manage to do all those measurements, that'll be a good step forwards.